to also take you guys through what the proving space looks like and what the hardware space looks like. We have Michael Gao, as I mentioned, from Fabric, who's been building a very custom VPU to accelerate real-time proving for Boundless and ZKVMs around the space. So welcome, Michael.
Thank you. All right, hey everyone. I'm Michael. I'm CEO and founder of Fabric Cryptography, and today I'm going to talk about how we're making risc-v ZKVMs real-time with Boundless and VPUs. So a little bit about what we're talking about here today. RISC Zero ZKVM is extremely sophisticated, like any ZKVM today. It has recursion circuits. It has many layers of recursion. It has lots of proving steps. And so, we build hardware, right? We build custom chips that are general purpose chips that are designed for cryptography. And that's quite a challenging task. This is not exactly a Bitcoin kind of thing where you have SHA-256, which is like a pretty, simple hash function, and you just tile that a bunch of times, and that's your ASIC, right? We're not talking about the ASIC kind of regime here. We're talking about a workload that is very, very sophisticated. Now, everyone here can understand why it matters to accelerate ZKVMs, but it's been regarded as largely, almost an impossible problem for a while. Actually 2 years ago when we were first pitching VCs on Fabric Cryptography, people actually thought that we were insane to, attempt to do a general purpose chip. Because a general purpose chip has to support all of these different parts. And so a little walkthrough through, RISC Zero's ZKVM, right? This is from an NVIDIA Nsight trace from an RTX 4090 that RISC Zero ran its workload on. Frank would probably want me to tell you guys that this is on an old version, so the new version is a little bit optimized. But regardless, there are both parallel and CPU portions. So actually, the GPU is doing the green parts because they're massively parallel, and the CPU is actually doing the red parts because those parts have to run on the CPU because of their inherent sequentiality. And so oftentimes, it's not just a problem of how do you make the compute super fast. It's also an issue of data transfer, right? Actually moving data from the CPU to the GPU and back again takes up a whole lot of time in an end-to-end ZK workload. And this is why a lot of people out there are pessimistic about hardware acceleration. People say, hey, what about all of the problems aside from chip design that you have to solve, right? Now, a little bit about how this is done right now, right? So right now, if you have a GPU server, you have a CPU, which is really, really good at heterogeneous workloads, right? Really, really good at sequential workloads, where you have to run one step and then another step, and then every step depends on the previous step, right? GPUs are really good at massively parallel workloads, where no one line depends on another line. Right? So if you need to do the same thing a million times and none of those times have dependencies on the other times, use a GPU, right? And so for example, if you think about witness generation, a CPU is very good at that because every clock cycle needs to run after the previous clock cycle. A GPU is really good at things like NTT and things like hashing because those are massively parallel portions of the workload. Now, thankfully, as professional computer architects, we at Fabric have seen this problem over and over again, right? Most of our team actually comes from the AI hardware industry, where we've seen firsthand, data movement problems, we've seen parallelization problems, we've seen different ways to slice data and lay out data. And so these are problems that we're actually accustomed to doing. Actually, one of my previous companies was an AI hardware photonics company. And so we're very familiar with this problem. And what we have come up with is an architecture that basically can accelerate the whole end-to-end thing. So it can do parallel arithmetic. Like a GPU, it has high performance like an ASIC, so we've designed it with minimal performance overhead compared to an ideal fixed function ASIC. Big claim. And it's flexible like a CPU. And it's all on one chip. That is what we call the Verifiable Processing Unit. It's basically a GPU designed from the ground up for cryptography. So it's a custom chip, and it is our custom chip coming early next year. So a little peek inside the chip, you've got high-speed memory, you've got a PCIe interface, but the most important thing is that we actually have a RISC-V 8-core processor on the chip. And so for all of that data movement stuff, you don't have to go off chip. You don't have to go through PCIe. The big advantage of our chip is you just use the RISC-V. And so this yellow part is an ultra-fast terabytes per second network on chip that's able to shuttle data around at terabytes per second without any bottlenecks. For comparison, PCIe interfaces typically run at tens or low hundreds of gigabytes per second. So way, way slower than what our network on chip is capable of. And then if you look at the arithmetic part, the green part, it's got these cores that are kind of like a GPU. They're massively parallel, but they've got an instruction set that basically is only focused on number theory. So they do modular arithmetic really well in prime fields. They can do anything from M31 to Goldilocks to Baby Bear to any prime field you can think of, they basically can do that. And so unlike a GPU, which uses only 10% of its circuitry on integer operations, we use all of our circuitry on integer operations. And if you look inside one of those green things, right, one of our tiles, our fundamental processing element, we've got an instruction cache, we got scratchpad memory, we've got a register file, and then we got a ton of integer arithmetic. So basically, this is the fundamental unit. We've got thousands of integer modular multiplication and addition operations across the chip. And we've got an ultra high-speed network on chip, so whereas a CPU communicating with a GPU might have to go through tens of gigabytes per second of PCIe, you can use our 7 terabyte per second network on chip to communicate between GDDR, PCIe, and the CPU. And here's the thing about ZK circuits. They're changing all the time, right? So actually, the last commit to the circuit was actually August 2nd, right? So these change every couple months, every couple weeks. And the awesome thing about the VPU being a programmable processor is we can adapt quickly to those updates. We have an on-chip RISC-V CPU. We have a massively parallel programming model. And so whether it's something happening in the tiles or something happening in the CPU, we can actually instantly adapt those changes. An ASIC would just become a paperweight, right? Like if you have a Bitcoin miner and Bitcoin switched from SHA-256 to Ketchak, the Bitcoin miner wouldn't do anything anymore, right? The awesome thing about the VPU is it's programmable. It can adapt to these changes, not just in the circuit, but even in the proof system. And we've got a cryptography native instruction set that we've co-designed with collaborators like RISC Zero. So we've had custom VPU instructions that are capable of doing these things with high performance. You see all of the different things, from MSMs to NTTs to Poseidon hash functions, Ketchak. It doesn't matter what you're doing in the field of ZK, you've got the ability to do it with super, super high performance. And specifically, RISC Zero runs on the Baby Bear prime field. We got that natively. And so in one instruction, you can do a multiply and accumulate with a Baby Bear prime field. Many of you are probably asking at this point, okay, give me the benchmarks, right? So this is a benchmark that we did on the toughest part of the RISC Zero workload. It is the eval check component. Eval check is this file that looks super, super complex. It's basically almost randomly generated like prime field and prime field extension instructions. And basically, we are able to get 10x over an RTX 3090, which is on a more advanced process node. So for those of you unfamiliar with chips, 12 nanometer to 8 nanometer to 5 nanometer is actually a really big discrepancy in the density of the transistors on the chip. So with far fewer transistors running at slower speeds, we're actually still able to compete with NVIDIA's 5 nanometer and post incredible results. Now, in terms of the future, there's a lot left to do. You know, the great thing about the VPU is it's not a one and done fixed function ASIC. It can improve over time because new changes in the proof systems can be adapted to the VPU. And so one thing really interesting is right now to do witness generation, you have to run, essentially, you have to simulate a RISC-V instruction set on an x86 host processor. That's what you have to do in order to do witness generation in any RISC-V ZKVM currently. So the awesome thing is we have a RISC-V on chip. What if we just use that and we bare metal ran all the RISC-V instructions through the RISC-V on our chip, right? You might be able to get the lowest latency ZKVM in the world. That's something that's really interesting for us. You know, we plan to evolve with RISC Zero. So as new circuit changes come out, you know, the ZerGen backend is going to have a backend for the VPU. We're going to be able to generate code automatically for future circuit evolutions. We're going to have software upgrades as the proof system evolves. You know, whether you're thinking about Binius down the road, GKR, or any other proof system down the road, multilinear versus, you know, basically we can adapt to all of those different proof systems. And the VPU Gen 2 is kicking off its design right now because Gen 1 is close to taping out. And so we'll also launch a hardware-software co-design effort with our collaborators of next-generation proof systems towards the next-gen VPU. And of course, we have orders of magnitude performance improvements left on the table. You know, as we move to 7 nanometer, 5 nanometer, and 3 nanometer, you know, we're going to be able to get orders of magnitude even beyond the current performance that you saw on the screen. So yeah, that's our plans to accelerate RISC Zero. If any of you have any questions, happy to take them.
Hello. So how does it compare to the Grace Hopper architecture, which has its own CPU, like 80-core CPU on the same package?
So unlike the Grace Hopper, the question was, how does this compare to the Grace Hopper GPU from NVIDIA, which has a GPU and a CPU on the same package? And that's a really good question. The answer is, number one, is way cheaper. You know, one of these cards is not $35K, which is the cost of a Grace Hopper. And number two, you know, the CPU and the GPU on the Grace Hopper are on the same package. The CPU and the VPU on our chip are actually on the same chip. So they are co-located on the same silicon. We can use the wires embedded in the silicon to actually send data between the CPU and the VPU. So that's a much higher bandwidth, basically, than you can achieve on the package. You also had a question?
Can you explain a little bit more about the circuit backend? And like, I'm just curious about how do you handle the hardware stuff that if the circuit system or proof system evolve, how do you handle that? Can you unpack a little bit more?
Yeah, that's a great question. So the question was basically, how do you actually handle changes in the circuit or proof system? So we've got several components of that. If the circuit changes but the proof system stays the same, most of the prover we don't have to update, right? All we have to update is basically the trace generation component and the witness generation component, right? Like all the stuff that updates when the circuit updates, right? So although the operations on the trace table don't change, the trace table generation itself has to change, right? And that's what ZerGen does right now for RISC Zero. So RISC Zero has this thing called ZerGen, which basically takes a circuit and automatically turns it into a GPU kernel or a set of GPU kernels. You know, we would have a similar thing that happens on top of ZerGen to be able to take that same IR to a vectorized VPU implementation. So that's kind of the first part. Now, what if the proof system itself changes, right? That's your other question. Well, then you just write a kernel for the VPU, right? So basically, it's kind of like the GPU in that you just write new software to support that new proof system. So it's not overnight, but you can write new software, and it's much easier than programming an FPGA. Right, FPGAs, you have to place and route new RTL on the FPGA. It's basically like a mini chip tape out. You don't have to do that. This is much more like a GPU where you're writing software, not hardware. Any other questions?
Would this be manufactured in a regular CPU fab? And how much would that cost? Because I don't think too many would be produced, and the cost might be super high.
The question is whether it's manufactured in a typical CPU fab. It's manufactured at TSMC, so we're on TSMC 12 nanometer. You know, it's used not just for CPUs; it's used for a bunch of things. And you know, while it does start out expensive, you know, in absolute dollar terms, it's actually much more cost-effective, both in OpEx and CapEx, than an NVIDIA GPU deployment by, you know, several times. So, you know, compared to 4090s, 3090s, it's much more cost-effective. If you just care about dollars per proof, like this is going to be cheaper and it's going to be faster.
How we will integrate that new chip into our current servers? Will it be some kind of system like, for example, Google with his Google Coral TPU to integrate directly using PCI Express, or will it be a specific ASIC?
Yeah, so I think your question was, how do you integrate this into a server? So the answer is we actually designed the whole server. So, you know, initially we're going to sell entire boxes full of VPUs. Now, we also design a PCIe card. So as time goes on, you can put like a different heat sink on the PCIe card, and you can have active cooling, and you can plug it into a consumer desktop, and it should be able to work. Now, for simplicity reasons, we can't start out that way. We have to start out controlling the entire system design. But then as time goes on, we'll have the resources and bandwidth to be able to like support different configurations as well, like that. And then in the far future, actually not so far, in the near future, you know, it might be possible also to have a consumer SKU where you can plug it in at home, and it will be very accessible to people.
Any more questions? Good. All right, let's thank Michael Gao for his time.
All right, thanks everyone.